Hello everyone and welcome to this new episode of our ISO tutorial series. Today I want to do the prep work so we can implement pathfinding from the next episode onward proper. And for me that means I want to do two things today. I want to refactor the map we have here, which is just an array of heights that was also part of the game scene, into a proper map data structure. And I also want to distinguish between 3D and 2D vectors. The reason for refactoring the map out of a game scene is because I want to be sure that we can add the pathfinding code to the map, as well as add more functionality and value to the map. And I want to distinguish between 2D and 3D vectors because I want to be very explicit when we're thinking about 2D and when we're thinking about 3D. So 3D is very relevant when we're talking about positioning in space and, for instance, positioning tiles on the correct place. These are using 3D. But our map in itself will only know two-dimensional coordinates and an elevation. So in a proper 3D map, you would have the option of, for instance, having holes or having different layers. That's not something we're doing here. We have a map that's comprised of an X and a Y coordinate, and when asked for an X and Y coordinate, you can get back a tile and an elevation. But there's no sort of going underground or going over the map in any way. So that's why I want to distinguish between 3D and 2D vectors, and the vector we have so far in our IsoConverter is actually a 3D vector. So the first thing I'm going to do is I'm going to rename this one into vector 3D, and this should change all the usages of this vector. So let's do a quick build and test to see if they were all caught. So all the tests are still passing, but that's not really a surprise because we only renamed this structure. So I'm also going to create a separate file for the vector 3D. And let's see. So let's take our IsoConverter of vector 3D. And copy all this stuff here. So we now have a 3D vector also in its own file. So now we can start thinking about a map. So to get started, I'll very quickly create a new file called map.swift, and this will house a structure called a map. And we'll add more stuff later on, but we also need a file to store map tests. So let's create a new Swift file called map tests. This one requires exe test, and this requires the ISO tutorial as a testable import. I'll have a final class, a map test, that inherits from test case, and now we can start writing our first test. So let's see. So let's think. What should be our first test? Well, I can imagine that if we map might know from itself how high it is and how wide it is. That also helps when going, for instance, through each and every tile. So that's a bit hacky solution here. So what I want is I want to make sure that we can do something like an empty map as a 0 width and height, because what I want to do is I'll have a map And then I can assert that map.goalCount is 0. And row count is 0 as well. These of course don't exist yet, but we can create them. Let's add another editor next to it so we can do it side by side. So let's just create a call count property and a row count property, and the test should now pass. Okay, that's not very exciting yet, but let's say we create a map based on the height map. Then I expect the height and width to be determined by the size of the height map. So let's create a new map. And this should take a height map. And a height map can be an array of integer arrays. So let's create a simple height map. So let's say, for instance, the first row is just ones. And it's a bit tedious seeing me copy paste this one over. So let me just get this, copy paste this one over elsewhere. Just a moment. So this is just a very basic height map. It's mostly flat, but it has some mountains or hills or cliffs, or give it a name in the middle. There's some difference in elevation. What we want, it's not really about the exact way the height map looks. What matters is the width and the height. So let's assert that the row count equals our height map rows. That's 0, 1, 1, 2, 3, 4, 5, 6. And we can do something similar for the call count. 1, 2, 3, 4, 5. So it's 6 by 5 big. And let's see. So this doesn't build yet because we don't have an initializer that takes in a height map. Let's add that one. So we still need the original one as well as a new initializer that takes a height map. That's an array of integer arrays, and that sets, and that should now at least build, but the test won't pass yet. So let's refactor this a bit. So we'll just define these ones as integers. We can set their values manually in the empty initializer. But for this one, we'll say the row count is height map count. So that's the number of rows. And the call count can be our height map first count, or 0 if for some reason that one doesn't exist. So let's see if the test now passes. Okay, so it passes. Let's continue. So what's the next thing that we want to make sure that the height map does? So let's imagine that we want to get the eventually get the height or the elevation back from the map if we pass in a coordinate. And I think it would be cool if you could do something like we have a map and then pass in something like an X or Y value, and then we get back our elevation, or this could be a vector of some kind. So let's start. What happens if we request a coordinate that's outside of our map? So let's say we have a test that says our subscript. That's the way we can get data by by what I just showed by doing something like this. This is called a subscript, and let's say it returns a negative height for a coordinate outside of the height map. So of course we again need a map. This map needs a height map. What I will do is I'll take this height map and I'll make it a fixture of this test class. This way we can easily reuse it. So now we need it here as a self.example height map. We don't have to copy it around each time. Then we'll say is for a test coordinate in, and now we need some coordinates outside of our height map. And what do I mean with that? Let me quickly show you. Let's say we have a map. And for instance, our coordinate here is 0, and this one is our width -1, height -1. Then I want to test some coordinates outside of this map. So for instance, we can have, let me just move this one around a bit. Let's add this one here. So let's say we want to see and look at this coordinate. This coordinate will be our width and the height +1. And we can do something similar on the other side. This will be our width +1, height and height. This one can be width +1, height +1. The same happens for negative values on the other side. So I created a couple of example coordinates, and I'm just going to copy paste them in. So let's go back to our test. Let's add some fixtures. So we have an example set of coordinates outside of the map, and these will be vectored to these. And oh dear, we haven't defined a vector 2D yet, but that's something we can quickly do. So let's create a new file called vector 2D, and the vector 2D should at least have an x coordinate and a y coordinate, and that should at least make this one somewhat happy. Okay, so we have the absolute minimum now to at least satisfy this requirement. So now we can say for each test coordinate in coordinates outside of the map, we can try and start testing a bit. So we'll assert less than that for our map that takes in a vector 2D for test coordinate x and test coordinate. As a test coordinate is a vector in its own right, I guess. Quick check, yeah. So we should just pass in the test coordinate, and then we get back a value less than 0. This doesn't work yet because for two reasons. Well, first off, we haven't defined a subscript on map yet, and also we can't use the vector 2D yet because then it needs to conform to hashable. So let's do that. And let's start creating the subscript function. So we'll say we have a subscript that takes in a coordinate type vector 2D. and this returns an integer. And guard, let's see, chord dot x should be larger than 0. Chord dot x should be less than call count. Chord dot y should be at least 0 and less than row count, else return -1. Otherwise we can return any value. So let's see if our test works. This one wants these. Well, let's try, by the way, make sure that we can compile first and see the test fail first. In essence, not compiling is also a red state, but I think it's always nice to really see the test actually fail first. Let's try again, and our test passes. Okay, so let's continue. We're not really using the heights yet. So that's a bit unfortunate, I guess. So let's do that now. Let's go back to our text, and let's create one that the subscript returns height or elevation, give it a name, for coordinate within height map. This again needs a map. And then we can go through each row. And each column. And then we can assert that our map add vector to the x and y. Add col and row equals example height map at row col. So let's run the test. This should fail because hard coding return value of 0 for valid coordinates. We need to somewhere store the elevations, and to do so we'll create a new property called tiles. This will be a map of 2D vectors to an integer where the integer represents the elevation. For the empty constructor, we can just use an empty dictionary. And for this one, we should go over each row and each column. And then determine the elevation. And then store that value in a variable called tiles. So we'll create an empty one here first. Then we can take this one, add the elevation to it, and eventually make sure that we set our own tiles to the loaded tiles. And now, instead of doing all this complicated stuff, what we can do is get rid of this for a bit. We can just look at our tiles, pass in the coordinates, and provide a default value. That's when it's a tile we can't find, and then return the negative value. So now the test passes, and we can get rid of this stuff, so it actually cleans up the code a bit. So let's go back here. So we have now a way of storing and retrieving height values. I want to Also make sure that we have a function to quickly transform within a coordinate or within the map a coordinate to from a 2D coordinate to a 3D coordinate by using the allocation. So let's create a test for a new function which we call convert to 3D, and we make sure that this x and y stay the same as the input. So the test will be something like this. So we will have our map again with our height map. Let's say we go from -3 to 3. We create a coordinate. And then we create a result. That's our map convert to 3D. Although this function doesn't exist yet, this is taking the coordinate. And we will assert that our result matches the coordinate. So the result of x should match coordinate x, and y should match coordinate y. So let's implement this function real quick, or at least a stop. Takes in a coordinate, type vector 2D, and this returns a vector 3D. For now, let's just return a 0. So now this compiles, but the test fails. So let's implement this function. Fortunately, not very difficult. This just creates a new vector 3D based on chord.x, chord.y, and the subscript value that returns the elevation. So if we now do this again, this should now pass. But we're not testing yet whether we get the correct elevation back. We did test for that one very quickly too. The Z property is the elevation. So again, we need our map. Well, we need almost all the same stuff, except that we assert that the Z value is the same as the subscript value from the map. How this passes. We can do a few quick refactor actions. For instance, we have a vector 3D. We can create a variable called xy that basically converts this one to a 2D vector. This will just return the x and y coordinates. So now we can refactor this test a bit. Okay, now we have the map and the new vector types. We can refactor some of the existing tests in the ISO tutorials. So in particular, we have here world coordinates that are converting back to screen space coordinates. And I think because we are expecting 2D coordinates here, it would be much nicer if these are actually 2D coordinates, and that our function converts world to screen actually returns a 2D coordinate. So these can all be 2D coordinates. And let's get back to the test. This first step should now compile. And let's see, did you already notice that convert world to screen now has 2D? Right, okay, so we are having an issue here that we try to add 2D coordinates together and also multiply them by a scalar. So we are missing the functions we have in our 3D vectors, these ones. We miss these in our 2D vectors. So let's copy them over and let's add them. However, these now are all based on 2D. Also, it looks like we have for the 3D ones actually a bug, so let's fix that in a bit. So we can now multiply vector 2D by a scalar as well as add them together. Let's go back to our 3D one. Notice that we're not setting a z value here. So that's apparently we don't have any tests that are covering this. But the chances of us forgetting later on while we see it now makes it valuable to just do it right now. So now we should be able to continue a bit further. So our build is successful. Let's see if let's see, we have some more that are now requiring 2D vectors. And most likely we will have to use simply change each time we build and look at the errors we get back to fix this. So these again are screen space coordinates, so these need to be changed as well. And let's see how far we're getting. So it's now building. Okay, so our tests passed. Let's look into our map for a bit if there are any other strange places. I'm sorry, our IsoConverter, if there are any places where we expect 2D coordinates instead of 3D coordinates. This one is fine. Rotate coordinate is fine as well. Now, this should be okay. So I think that's enough for refactoring. Let's go back and use our new map in the game scene. Okay, so we have a map. Let's use it. So we can go into our game scene and start using this map. So we here have the height map. I'm going to change the height map to a map that uses this height map. So this will break some of the code. In particular here where we're going through and showing the map. So instead of a height map.count, we can do a map.row count. And this one can be our map.call count. The elevation is our map, but then taking in a vector 2D for x and y. So we have now this one as well. And let's see what else broke. To move the entity to a random position. So what we can do is we can still use the x, but this can now be our map.call count and the map.row count. And this one, our position, can be our map convert to 3D. We pass in a 2D vector for x and y, and then we get the 3D one back, and we can redraw. So let's see if this builds and runs. We can still move them around, can still rotate. Rotate the map. Cool. So that's it for this week. So we created uh, two new vector structures. We changed the one we already had to make explicitly 3D, as well as create a new 2D vector. And we created a map that stores all the data related to the terrain of our game, and perhaps stuff more. It's in the map that from the next episode on, we're going to implement the pathfinding functionality. And yeah, that should be really cool. So thanks for watching and have a good day.